Hi, my name is Lauryn Takanishi, and today I'm going to share with you a bit of my research from this year. My main goal was to measure the carbon dioxide levels of classrooms and cars as an indicator of air ventilation quality to determine the risk factor of catching an airborne virus such as SARS-CoV-2, which is the virus that causes COVID-19. Recently, there has been an increased concern and awareness about indoor air quality and the detrimental effects on people due to high concentrations of carbon dioxide. The demographic focus of my research is much more specific. Indoor air quality in classrooms and cars for students because they spend most of their time in those locations. High concentrations of carbon dioxide in a classroom negatively affects the work performance and health of students and teachers. The outdoor level is 410 parts per million, and at 1,000 to 2,000 parts per million, people become drowsy. Anything above 5,000 parts per million is considered hypoxia. Improving ventilation in varying environments will allow people to work at their greatest potential without being negatively affected by poor air quality and lack of air circulation. My goal is to determine if air conditioning and ventilation systems in classrooms can maintain a healthy level of carbon dioxide throughout a 40-minute time period. According to the World Health Organization, COVID-19 was declared a pandemic in March 2020. Being aware of one's safety of one's environment is crucial, especially during a global pandemic. Because SARS-CoV-2 is an airborne virus, scientists recommend being in well-ventilated environments. Increasing the air ventilation rate reduces the spread of airborne virus transmission. According to a study in a tuberculosis outbreak in Taiwan, carbon dioxide levels under 600 parts per million completely eliminated the tuberculosis virus. Connecting these ideas, measuring carbon dioxide levels can be used as a proxy for air quality and ventilation to determine the potential risk of catching SARS-CoV-2 in a set room. For a period of time, children did not attend school in person because of COVID-19. Research later showed that children are less likely to be severely affected by COVID-19, so going to school during the pandemic became possible. Although there is still a risk, the benefits of attending in-person school outweigh the costs. However, the level of safety of carbon dioxide is unknown with the use of personal protection equipment. I do not know how wearing PPE changes the rate at which carbon dioxide levels increase. Keeping schools open is necessary because it allows students to socialize, be active, have access to educational materials, and learn. Overall, the purpose of this research is to communicate the importance of being in environments with good air quality in order to maintain one's health. There are multiple variables that play a role in determining the rate at which carbon dioxide levels increase. The number of people, physical activity, opened or closed doors and windows, size of the room, and additional air ventilation systems must be considered while measuring the carbon dioxide levels. The Wells-Riley equation shows that the higher the air ventilation rate, the more rapidly particles will decay in the air. The probability of infection through airborne viruses is inversely correlated to the ventilation rate. This equation shows that there is a relationship between air ventilation and the rate at which airborne viruses particles disperse and decay in the air. When there are more people in a room, carbon dioxide levels increase. Finding a way to decrease carbon dioxide levels in a room or environment will make sure that while there can be several people in a room, the carbon dioxide levels will not exceed the levels that are considered harmful or dangerous. My research project will answer this question. What are the levels of carbon dioxide in places where students spend the most time? For my experiment, it would take place in classrooms and cars. I hypothesized that the carbon dioxide levels would be below 1,000 parts per million, the level at which students tend to lose focus in the three classrooms. Knowing that classrooms have a good air ventilation system will ensure that students will be learning in a healthy and safe environment. Students spend most of their times in classrooms throughout the day, so I wanted to measure the carbon dioxide levels in that environment. The experiment will also take place in a car to determine how fast the carbon dioxide levels increase in a small space with no ventilation system and closed windows and doors. From the experiment, issues such as preventing poor air circulation, improving air quality, and making sure that students, teachers, and drivers are breathing good quality air will be addressed. The carbon dioxide sensor, designed and provided by Dr. Rick Stulin and built by Ethan Hui, will be used to measure the levels of carbon dioxide in a room after a set period of 40 minutes. The carbon dioxide sensor calculates the average level of carbon dioxide every 15 seconds and displays it while continuing to update and provide more data as time goes by. It was calibrated to 410 parts per million, which is the average outside air level. The carbon dioxide sensor will measure and show the carbon dioxide level of the room in time increments and segments from 0 to 40 minutes in a room with a set amount of people. In 3 different classrooms, experimental trials were conducted in order to determine if these classrooms' carbon dioxide levels are below 1,000 parts per million and can maintain those levels throughout a 40-minute period. To collect and analyze more accurate data, 9 replicates of the experiment will be performed in each classroom. In a class period of 40 minutes, carbon dioxide levels will be recorded in the time intervals. The carbon dioxide level will be recorded 6 times throughout the class period in order to estimate and graph the rate of change in the carbon dioxide levels over time. In all 3 classrooms throughout the entire 40-minute period, students will be having light discussions, sitting at their desks, and wearing masks and face shields. Keeping track of the students' activity level is important in the experiment because an increase in physical activity will also result in an increase in carbon dioxide. In a small classroom, the windows and doors will be closed with 12 people in that room. In a medium-sized classroom, the windows and doors will be closed, but there will be a total of 14 people. And in a large classroom, the windows will be closed, but 2 doors will be open and there will be 8 people in that room. Analyzing the classroom dimensions, conditions, and number of people in that room is a key factor in determining the ventilation rates. This next suggestion for further experimentation involves conducting a similar experiment in a small, medium, and large car. The experiment procedures will also remain the same, but it would take place in a more smaller and compact space than a classroom. One person will be in the car for a total of 20 minutes. The windows and doors will be closed while the air ventilation system will remain off for the entire period. Performing the experiment in a car will make people aware that carbon dioxide levels can increase at a surprisingly fast rate in smaller spaces if air ventilation is poor. In all 3 classrooms, there were similarities between the collected data and patterns shown in Figure 1. All 3 classrooms showed a common trend, which showed a direct relationship between carbon dioxide and time spent in that room. As more time elapsed in each classroom, the carbon dioxide levels would rise higher than the previous recorded time increment levels. In the 3 classrooms, there was a significant variation of carbon dioxide levels and the rate at which they increased with time between each of the rooms. In the small room, there was a 140 parts per million increase across the 40-minute time period. However, in the large classroom, there was a 39 parts per million increase across the 40-minute time period. Though the small and large classrooms were similar in the carbon dioxide levels, the small classroom had a higher average increase in carbon dioxide than the large room in the 40 minutes. This suggests that the large room had better air ventilation than the small room. Another thing to consider is that the large room had closed windows and 2 open doors, while the small room had closed windows and doors. Additionally, there were 4 less people in the large room than the small room, which may have been a contributing variable that resulted in a smaller increase in carbon dioxide levels across the 40-minute period. However, the medium room had a significantly higher carbon dioxide levels than the other 2 rooms. Not only were the carbon dioxide levels collectively higher than the other 2 classrooms, but the increase in carbon dioxide during the 40-minute time period was 247 parts per million. There were also 14 people in the classroom, and the doors and windows were both closed. This could be a reason why carbon dioxide levels and the rate at which the carbon dioxide levels increased were so high. Although there were differences in data in the 3 classrooms, they all shared a direct relationship between carbon dioxide levels and time. In all 3 cars, there were similarities between the collected data and patterns shown in Figure 2. Based on the collected data from the 3 cars in Figure 2, the carbon dioxide levels increase at a high rate when there's no air circulation in a short period of time. This trend in data supports my hypothesis. All 3 cars share a common trend which showed a direct relationship between carbon dioxide and time passed in the car. As more time elapsed in the car, the carbon dioxide levels would increase higher than the previous recorded time increment levels. Driving with the windows up and the air ventilation system off is hazardous to one's health because of the rapid increase in carbon dioxide levels in a short period of time. For the car data in Figure 2, there are not many differences between each car's data. All 3 sets of data range from around 500 to 900 parts per million, and their trends were the same for each car. The difference between the highest and the lowest car's carbon dioxide averages was only 60 parts per million. Generally, the data across the 3 cars did not vary to a significant degree. Collecting carbon dioxide levels in 3 classrooms gave me an estimate to determine if the air ventilation systems are effective enough to maintain carbon dioxide levels that are lower than 1,000 parts per million. Opening the doors or windows in a classroom that is at 1,000 parts per million and above all the time will significantly decrease the carbon dioxide levels. The spread of airborne viruses could not be determined by the carbon dioxide levels because of the use of PPE. I don't know exactly how much the use of PPE is reflected with SARS-CoV-2 transmission. However, the article regarding the tuberculosis outbreak states that the environment with levels under 600 parts per million can eliminate the transmission of tuberculosis, even without PPE. Therefore, the use of PPE is essential in preventing the spread of airborne viruses. Conducting the experiment and doing this research will help spread awareness that the quality of air people breathe directly affects their health. In addition, safety in classrooms, cars, and homes is important, and the concentration of carbon dioxide should be at suitable levels for inhaling in order to prevent hypoxia. Further research may include adding plants to a room because they reduce carbon dioxide levels and increase oxygen in the air. I predict that carbon dioxide levels will increase at a lower rate. Seeing the impact of plants may spread awareness that having plants in buildings is effective in improving one's health. To anyone who is interested in studying independent research next year, I advise you to keep track of your articles, sources, and references so you don't get overwhelmed. Don't procrastinate and work around the due dates to stay focused. Also, pick a topic that you're passionate about because it will motivate you to keep gaining knowledge as you progress. I learned how to write a research proposal, abstract, and final research paper with an annotated bibliography while collecting reliable sources for support. In my opinion, the most important part about research was collecting and analyzing the data. Thank you so much to Dr. Chan for guiding me through the research process. Thank you as well to Dr. Stulin for designing and providing the carbon dioxide sensor. And finally, thank you, Ethan Hui, for building the carbon dioxide sensor for me to use. Here's my works cited, and thank you so much for attending and listening to my presentation.